today I am going to continue with the concepts of molecular orbital theory. In the previous session, I discussed postulates and how actually BMO and ABMOs are formed. We'll learn some particular examples and related properties associated with molecular orbital theory. First, you need to know the energy level diagram for molecular orbitals. So let me consider the energy level diagram. Let me write here energy level diagram of molecular orbitals. We know that atomic orbitals combine and molecular orbitals are formed. There are two types of molecular orbitals are going to be formed. One is bonding molecular orbital and one more is anti-bonding molecular orbital. As we know, we need to follow some standard rules for filling up of electrons into the atomic orbitals like Aufbau principle, N plus L rule, Paulis exclusion principle, Hund's rule and extra stability rule. Now I am going to consider energy level diagram first and later we will analyze how actually energy level sequence has to be considered while writing the electronic configuration in case of molecular orbital theory. So now I am going to consider oneness atomic orbitals first. So oneness atomic orbital I am going to consider here. So let me draw the diagrams and we'll see explanation meanwhile. So here this portion is for atomic orbitals. AO stands for atomic orbitals and here also AO stands for atomic orbitals. Atomic orbitals combined and we get molecular orbitals. In general we follow the same fashion. We know that one. While filling the electrons, we have to fill oneness atomic orbital first, later 2s and 2p, and the energy level will increase in the same fashion in molecular orbitals also. The same rules should be followed. So this is the atomic orbital. I will represent atomic orbital by in this kind of a circle. You can consider square box also for representing. It is left to you. However, the theory is the same for these two. So oneness atomic orbital and this is oneness atomic orbital. We know according to the postulates of molecular orbital theory, atomic orbitals of same energy and same symmetry should combine, we get a molecular orbital. Oneness atomic orbital I have, same energy and same symmetry, therefore these two combine, we get molecular orbitals. One is a bonding molecular orbital and one more is anti-bonding molecular orbital. Energy of a bonding or molecular orbital is less, whereas energy of anti-bonding molecular orbital is more when compared with the energy of respective atomic orbitals. So therefore this molecular orbital is for bonding molecular orbital. I will write it as C because head-on or coaxial overlapping takes place, and this molecular orbital I consider it as sigma star, where sigma stands for BMO whereas sigma star stands for ABMO. In general, you remember, if we don't write anything, sometimes we write B that represents BMO and star represents ABMO, and these are molecular orbitals formed by oneness atomic orbital. Therefore sigma oneness I write here and here I write sigma star oneness I write here. So this is the molecular orbitals related to oneness atomic orbital. So after oneness we have 2s. So how I am going to represent that? So just observe here. This is for 2s. What I am drawing now, that is for 2s. Yes, 2s, yes, atomic orbital, only one atomic orbital we have. So this is for the 2s and this is for the 2s. When 2s atomic orbitals combine, we get two molecular orbitals. One is BMO and one is ABMO. Since we have SS overlapping, we get sigma and we get sigma star, and this is BMO and this is ABMO, and it is of 2s and it is also of 2s. That depends on the combining atomic orbitals. So now I am going to consider 2p atomic orbitals. So let me draw the 2p atomic orbitals over here. So try to know, for p subshell we have 3 atomic orbitals, and these are px, py and pz. The shape of s atomic orbital is spherical, whereas the shape of p atomic orbital is dumbbell, and all these are oriented in either x or y or z direction. We get a 2px, 2py and 2pz. So 3 you need to consider, 3 spheres I consider, and for p atomic orbitals I consider 3 spheres in this fashion. Okay, and this is 2p again, and this is also 2p, or you can write 2px, 2py, 2pz, and here you can write 2px, 2py and 2pz. So here in this case, the 2p atomic orbitals will overlap with the 2p atomic orbitals of same energy and symmetry. We get molecular orbitals. Then what kind of molecular orbitals we get? Let me draw over here. This is the 1 molecular orbital, and here we get 2 molecular orbitals, and in this energy level 2 molecular orbitals, and in this energy level 1 molecular orbital we are going to get. We'll try to name these. Okay, as we know, one is x and one is y and one is z here. So this is actually sigma, I write here, because there will be head-on overlapping, therefore sigma bond is formed, and these two, so one will be pi and one more will be pi. So this is for the pi and this is for the pi. So we have x, y and z. This will be sigma z, and here it is sigma x, and here it is also sigma y it is. So x, y, z I am going to consider here. So you can write 2p here, that is pi 2px, pi 2py and sigma 2pz also. It is left to you. We can consider any one of these. So here we have 3 bonding molecular orbitals. Now I consider anti-bonding molecular orbital. Since it is sigma z, and the above one, this should be actually sigma star z, and here it is pi x, and this is pi star x, and this is pi star y actually. So 3 anti-bonding we have and 3 bonding molecular orbitals we have. Try to know all these are in increasing order of energy. So energy will be increasing in this fashion. So this is how the energy level diagram can be considered. So try to know, this is for 1s and this is for 2s and this is for 2p here. Remember, in 1s we have 1 BMO and 1 ABMO. In 2s we have 1 BMO and 1 ABMO. In 2p, see here 1, 2, 3 BMOs we have, and 1, 2, 3 ABMOs we have. Because in a 2p atomic orbital we can separate it as 2px, 2py and 2pz. So out of these 3, one forms sigma bond by head-on overlapping, and 2 atomic orbitals form pi bond by sideway overlapping. So here I write sigma z, this is pi x, this is pi y. So here all these are bonding molecular orbitals. Whereas here I have written pi star x, pi star y, and these two are anti-bonding molecular orbitals. And one more we have, that is sigma star z, that is also anti-bonding molecular orbital. So this is in general, you need to remember how we can draw the energy level diagram for this. So by drawing this energy level diagram, you need to know how the atomic orbitals are in the increasing level of energy. So energy level sequence I am going to write. So first, as I mentioned, energy is moving from bottom to top. So the least one will be sigma 1s. So let me write here. So observe here, sigma 1s. I am going to write molecular orbitals, and after that we have sigma star 1s, isn't it? And next, after this we have sigma 2s. So sigma 2s, and after that we have sigma star 2s, isn't it? Next you come, here we have a sigma z. You can write sigma z or you can write a sigma 2pz also. As I mentioned, you can mention the atomic orbital sigma 2pz. So this is sigma z, that is for 2p, therefore sigma 2pz. And next we have pi x and pi y. So pi 2px and pi 2py. If you observe pi x and pi y, they are in the same energy level. Means the energies of pi x and pi y are almost identical. So therefore equal sign I represent, means these pi 2px and pi 2py are of same energy. So after that we have pi x star and pi y star. I am going to continue here. So pi 2px star and pi 2py star, and these two are in the same energy level. I can equate these two. And one more we have, what is that? Sigma 2pz star. So this is the energy sequence you can consider. So you need to remember the energy sequence in the same manner, because normally we write electronic configuration as 1s2, 2s2, 2p like that. Whereas in case of molecular orbital theory, we need to write electronic configuration in this fashion. That is the treatment of a molecular orbital theory. So this is how in general we consider. So we have some exception here. So if you consider some lighter elements, molecules like the boron or carbon and nitrogen, and here small change is going to be considered in case of energy level diagram. And what is that small change here is, let me write that first. So 1s we have as it is, and sigma 1s we have, and sigma star 1s, and sigma 2s, sigma star 2s we have. Whereas in case of lighter elements, lighter molecules of boron, carbon and nitrogen, so these two has to be interchanged, these two energies. So that is 2p z and 2px, 2py, they are supposed to interchange. So therefore first we need to consider pi 2px and it has same energy as pi 2py. Later you need to consider sigma 2pz and the remaining will be as it is, that pi star 2px, and the energy will be same as pi star 2py, and later we have sigma star 2pz. So try to know for first elements. So remember, usually hydrogen we have, and helium, lithium, beryllium, and then we get boron, carbon, nitrogen. So if you consider elements from hydrogen to beryllium, we fill the electrons in 1s atomic orbital and 2s atomic orbital. Beryllium atomic number is 4, maximum number of electrons is 4. So 4 electrons are going to be filled in 1s and 2s atomic orbital. There is no question of 2p atomic orbitals. When you go to the elements after beryllium, that is boron, carbon and nitrogen, there will be electrons in 2p atomic orbitals, and these are lighter elements. So in that case, this is the energy sequence you need to consider. So remember that here 2px, 2py comes first, later 2pz is going to come. So what is the reason why there is interchange of these atomic orbitals? This is the simple way how I told you to remember. The reason behind that is there is mixing of 2pz and 2s atomic orbital. So mixing of these. So 2s atomic orbitals, we have 2 electrons. Later the added electron will enter into 2pz. So there is mixing of these 2 atomic orbitals. Because of that reason, so this is the change in atomic orbitals, molecular orbitals you need to consider, and that is only valid for boron, carbon and nitrogen. And after nitrogen we have oxygen, fluorine, neon, and remaining all these, this is the energy sequence you need to consider. So in one very simple manner I will tell you, 1s this will be same and 2s molecular orbital will be same, and the only change we are going to observe in 2p molecular orbitals. Remember that if you have the lighter elements for p, you need to consider in this fashion. See here, for lighter elements you need to consider p atomic orbitals in this fashion, because exactly opposite of that, because as I mentioned, you need to interchange these two. isn't it? So you need to interchange these two. So we get this is the sigma 2pz and this is pi 2px and pi 2py. For boron, carbon and nitrogen, in P you need to consider this. I will write here, this is for boron, carbon and nitrogen. If you consider oxygen, neon and all these things, and in that case we need to consider the molecular orbitals in this fashion. So this is how we need to consider as same as the molecular orbital structure what I have done. So this you need to remember how to draw the 2p atomic orbitals. So try to know this is in general for lighter elements you need to consider the energy level in this structure. So remember that sigma 1s is the minimum and it goes on increasing in this fashion. That would be the molecular orbital treatment, and this is how the energy level diagram can be drawn. So if you know the energy level diagram of molecular orbitals, then we'll consider some examples and we'll try to know what would be the bond order in these examples. Let us know what actually bond order is. Bond order. If there is mutual sharing of valence electrons, covalent bond is going to be formed. If you count the number of covalent bonds present in between two atoms of a molecule, that is considered as bond order. In simple, you remember, number of covalent bonds in between atoms represents a bond order. Examples we'll see. If you consider a hydrogen molecule, we know hydrogen molecule, there is combination of hydrogen atoms, hydrogen molecule is going to be formed. So one shared pair of electrons we have, therefore one covalent bond is formed. Therefore the bond order in case of hydrogen is 1. If you consider oxygen as an example, and we know in between oxygen atoms we have two covalent bonds, because two shared pair of electrons we are going to observe. Therefore the bond order in case of oxygen is 2. If you consider a nitrogen as an example, as we know in between nitrogens we have a triple bond, therefore the bond order in a nitrogen is 3. So remember that the number of covalent bonds present in between the atoms of a molecule stands for bond order. So how it is 1, how it is 2 and 3 in case of hydrogen, oxygen, nitrogen respectively will study according to bonding molecular orbital theory. So before moving with that, we'll see one concept, that is isoelectronic species. Isoelectronic species. Here I use the word like species, means the particular maybe atom or ion or molecule. So instead of saying atom, ion or molecule, in general I use the word species. Isoelectronic species, species having same number of electrons. If you consider two or more atoms or ions or molecules, and if you count the number of electrons and number of electrons is same, then these species are considered to be isoelectronic species. So isoelectronic species, species containing same number of electrons. So if you have the collection of isoelectronic species, try to know the isoelectronic species are going to have identical or same bond order. Try to know that the bond order in isoelectronic species will be same. Example we'll see. So if you consider example of F2 and O2 2 minus, F2 is a molecule and O2 2 minus is ion, in particular anion. So what I am going to say, the final statement I am going to tell here, the bond order in F2 is 1 and the bond order in O2 2 minus is 1. The reason behind that, we can calculate bond order anyhow using one suitable formula, but these two are actually isoelectronic species, and isoelectronic species are going to have identical bond order. So first let us consider how actually these two are isoelectronic species. As I told, you need to calculate number of electrons. Fluorine, atomic number 9, protons is also 9, electrons is also 9. So 2 we have, therefore 9 and 9, 18 electrons we are going to get. So in F2 we have 18 electrons, whereas in case of oxygen atomic number is 8. Okay, 2 oxygens we have, so I will consider 8 and 8. 2 minus we have, so what it indicates? 2 minus anion. As we know, anion is formed by gain of electrons. So how many electrons it has been gained? 2 electrons. So 2 I will write here. So 8 plus 8, 16, 16 plus 2, what we have? 18 electrons. So if you consider F2 and O2 minus, number of electrons are same, therefore these two belongs to isoelectronic species, and the bond order of these two will be same, and actually the bond order is actually 1 in these two cases. One more example we'll see. I consider example of nitrogen N2 and carbon monoxide and NO plus. Okay, so we'll see whether these are isoelectronic species or not. Nitrogen atomic number is 7, therefore electrons will be 7, and 2 nitrogen 7 7 14 electrons we have here. Carbon 6 electrons we have, and oxygen 8 electrons we have, and 6 plus 8 14 electrons we have here in this case. So these two are isoelectronic species. What about this one? Nitrogen it is 7, oxygen it is 8, plus we have cation, plus there will be loss of electron. So how many electrons? 1 electron, therefore minus 1 I am going to write here. So now here in this case also the number of electrons will be 14. So if you consider the nitrogen and carbon monoxide and NO plus, the number of electrons in all these cases will be same. So these are isoelectronic species, and we know that one N2 in a nitrogen molecule the bond order is 3, isn't it? Now by this concept also I can say the bond order of carbon monoxide and NO plus will be 3, means in between carbon and oxygen we have 3 covalent bonds, in between nitrogen and oxygen we have 3 covalent bonds. So if you know bond order of one molecule, and if one more species we have, if the bond order is as same as the original one, then that will be definitely isoelectronic species. Actually in these cases the bond order will be 3 actually. So remember that if you have isoelectronic species, then the bond order will be same. The species containing same number of electrons, equal number of electrons, and they are considered to be isoelectronic species. And this is how in general what actually bond order stands for, and how we can compare with the species. Now in MOT we have a definite formula to calculate bond order. Let me write that. What is that formula to calculate bond order? So I am going to write here. Bond order can be calculated by, so bond order is equals to 1 divided by 2 into, I will write NB minus NA. This is the formula you need to remember. So bond order helps us to know some other properties of a molecule. So it is important to get the bond order for a particular molecule. That is calculated by this formula. Bond order is equals to 1 by 2 into NB minus NA. So what actually NB and NA stands for? Let me write here. NB stands for number of electrons in BMO, bonding molecular orbitals, and NA stands for number of electrons in ABMO, anti-bonding molecular orbitals. So now we know the energy level diagram of molecular orbitals, and electrons can be filled into the molecular orbitals. So if you count number of electrons in a bonding molecular orbital, if you count number of electrons in anti-bonding molecular orbital, and if you take subtraction of that, later one off of that, then you are going to get what actually the bond order. I told you how to identify BMO and ABMO. In the molecular orbital, actually ABMO is represented by this star, and BMO we just write sigma or pi, and sometimes we can write B also, it is left to us. However, we can consider any one out of these two. Remember, if you have a star, that stands for anti-bonding molecular orbital, energy will be quite high, and that is quite unstable when compared to BMO. So this is how the bond order formula you need to remember, that is the theory related to that. So now we'll consider examples, so that we are going to draw molecular orbital structure, we are going to calculate bond order, and what are the associated property for that. So now let me consider some examples for that. So let me write the heading. So the heading will be molecular orbital treatment, molecular orbital treatment of homonuclear diatomic molecules. So now I am going to talk about molecular orbital treatment of homonuclear diatomic molecules. So now I classify the molecules into two different classes. One is homonuclear molecules and one more will be heteronuclear molecules. Homonuclear diatomic molecules, diatomic, atomicity will be 2. Examples here, if I consider H2 as an example, this is a diatomic molecule. And if I consider O2 as an example, this is also diatomic molecule, and in these two cases atomicity is 2 because we have one hydrogen atom and one more hydrogen atom. They combine, we get a molecules like H2 and O2. Homonuclear, identical nucleus means same kind of atom we have. Later I am going to talk about a molecular orbital treatment of heteronuclear. Example, carbon monoxide, later I am going to talk. So carbon is one nucleus and oxygen is one nucleus, different atoms we have. Of course we are going to talk about diatomic molecules of the same kind, and that is considered to be heteronuclear. And now I am going to talk about homonuclear diatomic molecules only. Later we will see heteronuclear diatomic molecules. And the first example what I am going to consider here is the formation of H2 molecule, hydrogen molecule. This is the first example what I am going to consider, hydrogen molecule. First step will count number of electrons in hydrogen molecule. Later we'll draw the molecular orbital treatment energy level diagram. We'll write electronic configuration and bond order and the properties related to that. So how actually H2 molecule is formed? So let me write here. One hydrogen atom combines with one more hydrogen atom, we get hydrogen molecule H2. Atomic number of hydrogen is 1, means we have only one proton and one electron. The electronic configuration will be 1s1. One more hydrogen atom, that is 1s1. Totally in hydrogen molecules, how many electrons we get? So one from this hydrogen, one from this hydrogen, we are going to get 2 electrons, isn't it? So now you need to consider 2 atomic orbitals, one of 1s and one more of 1s. As we know, atomic orbitals combine, we get molecular orbitals. The main condition for atomic orbital, they should have same energy and same symmetry. So principal quantum number is 1, principal quantum number is 1, azimuthal quantum number, here we have s and here also we have s. They are going to combine. So in the energy level diagram, I am going to consider the part of 1s atomic orbital only, since in hydrogen we have only 2 electrons. So let me draw the energy level diagram of that. So observe here, I am going to draw the energy level diagram here, and this is okay molecular orbital, and this is the atomic orbital, and this is how I am going to link to represent the energies of these two are same. Okay, and here one orbital and one orbital, and molecular orbitals we are going to get here. This is the one molecular orbital and this is the one molecular orbital. As we know, this is atomic orbital and this is also atomic orbital. In the middle we have molecular orbitals. So 1s we have. So this is the 1s atomic orbital and this is the 1s atomic orbital. Remember, this 1s is of this hydrogen atom and one more 1s is of this hydrogen atom. They are going to overlap. So when atomic orbitals combine, we get a molecular orbitals. So this is bonding molecular orbital and this is anti-bonding molecular orbitals. S orbital overlapping, as we know, sigma bond is going to be formed. Therefore sigma will be here and sigma star will be here. Star represents anti-bonding molecular orbital. So this sigma is of 1s, therefore sigma 1s I write here, and this is sigma star 1s I write here. This is how you need to draw first a blank molecular orbital energy level diagram. So now we will fill the electrons. So in a 1s atomic orbitals here, 1s atomic orbital, we have only one electron. So one electron I am supposed to mention here. So one electron I write here. In this 1s atomic orbital, we have one electron. So here we need to consider the one electron. So one electron we have here 1s atomic orbital and one electron we have in one atomic orbital. They are going to combine. Okay, as I told, you need to follow the standard rules while filling the electrons. I hope you know all these rules. Let me explain that once again. Of Bohr rule. Electrons are going to be filled in the increasing order of energy level. First 1s we fill, later 2s we fill. In this fashion we are going to fill the electrons. Very important property is the Paulis exclusion principle. That stands in one atomic orbital, or if you consider molecular orbital, only 2 electrons of opposite spin can be paired. So if you have 1 electron here and 1 electron here, so these 2 electrons, totally we got 2 electrons. So in the one molecular orbital we have to fill only 2 electrons, that too of opposite spin only. So here I have 1 electron, totally 2 electrons I have here. So energy of sigma 1s is less when compared to energy of sigma star 1s, as I represented the energy level sequence also. First this has to be filled, 2 electrons we have, so 1 in this fashion and 1 in this fashion represents, and this is the 1 electron with the spin in the clockwise direction, plus 1 by 2 we can say, and one more will be of a minus 1 by 2, that is going to spin in the anti-clockwise direction. So electrons of opposite spin can be paired. That is actually the Paulis exclusion principle. So in a BMO we have 2 electrons and total 2 electrons and fill to 2 electrons. So ABU will be empty here. This is how the molecular orbital diagram for hydrogen molecule is going to be drawn. So now I consider what would be the electronic configuration. How to write the electronic configuration? As I mentioned, you need to consider molecular orbitals. First what we have, sigma 1s. So now let me write here sigma 1s. In sigma 1s, how many electrons we have? 2 electrons. Therefore bracket I write and superscript I write 2. And in case of this we don't have any electrons, so no need to write that also. Okay, so that is the electronic configuration of hydrogen molecule according to MOT, molecular orbital theory. Now we'll calculate what about the bond order. Bond order, what is the formula? 1 divided by 2 into NB minus NA. Okay, so 1 divided by 2, what is NB? Number of electrons in bonding molecular orbitals. So in between these, which one is bonding? This is the bonding molecular orbitals. How many electrons we have? 2 electrons we have. I write 2 here. Minus number of electrons in anti-bonding molecular orbital. We don't have any electron, therefore I will write 0 here. And if you simplify that, we are going to get what actually? 2 divided by 2, and we are going to 1, get 1. What is that 1? Bond order. Bond order is 1. What it signifies? In between 2 hydrogens we have 1 covalent bond. So what I'm going to write here, H, 1 covalent bond, and H we got here. That is the significance of bond order. Bond order helps us to know how many covalent bonds are there in between the combining atoms. So that is how we can calculate the bond order. Now using this molecular orbital diagram, we can guess what would be the magnetic property of a molecule. So remember that magnetic property. As we know, magnetic property depends on number of unpaired electrons, isn't it? So if we have unpaired electrons in atomic orbitals or molecular orbitals, and that particular molecule or a species is paramagnetic in nature. So remember that paramagnetism arises due to presence of unpaired electrons. If we have completely filled electrons, or if we have completely empty electrons, or I can say absence of unpaired electrons. So if there is absence of unpaired electron, that corresponds to diamagnetic in nature. This concept we know, it seems. So here if you observe molecular orbitals, so observe molecular orbitals, here we have pair of electrons. They are not unpaired, they are already involved in bonding. Unpaired means you should have single electrons in the molecular orbitals. So here it is empty, no question of that. Here completely filled molecular orbitals we get, therefore absence of unpaired electrons we have, therefore hydrogen molecule is diamagnetic in nature. Hydrogen molecule is diamagnetic in nature, means hydrogen molecule is not going to be attracted by magnetic field, or I can say hydrogen molecule is slightly repelled by magnetic field. That is the meaning of diamagnetism or diamagnetic property. And if you see unpaired electrons, let us assume we have one unpaired electrons, and we have one unpaired electrons, means that corresponds to paramagnetic property. So the substance which are going to be attracted, slightly attracted by magnetic field, that is considered to be paramagnetic, and the reason for that is the presence of unpaired electrons. So since we don't have unpaired electrons, therefore hydrogen molecule is diamagnetic in nature. This is how the concept of energy level diagram, the concept of bond order are supposed to be used to explain the hydrogen molecule according to molecular orbital theory. First we need to consider how many electrons we have, later we need to draw molecular orbital structure, then electronic configuration, bond order, and what is the property associated with that. This is how one very simple example I consider, that is of hydrogen molecule, to explain molecular orbital theory. Second example, He2 molecule, helium molecule I am going to consider here. One helium atom combines with one more helium, we get a helium molecule. Electronic configuration of helium 1s2, since atomic number is 2, 2 electrons we have. Here I have 1s2, and the total number of electrons in a molecule will be 4 electrons. 2 electrons from one helium atom and 2 more electrons from one more helium atom, totally 4 electrons we have. So 4 electrons has to be distributed in the molecular orbitals. So let me draw the energy level diagram of that. So these two are the molecular orbitals and these two are the atomic orbitals. So now we'll consider the atomic orbitals as well as molecular orbitals. This is the one atomic orbital and that is for 1s. This is for the one helium and one more helium we have, and here is also 1s we have. So these two are atomic orbitals, and in the middle we have molecular orbitals. 2 molecular orbitals are formed. One is BMO and one more is ABMO. This is a sigma and this is a sigma star, and 1s we are going to talk about. So 1s molecular orbital, 1s molecular orbital we have. So this is the energy will be increasing in this fashion as we know. Totally 4 electrons we have. So 4 electrons are going to be distributed in sigma 1s and sigma star 1s. Energy of sigma 1s is low, therefore first we have to fill electrons here and later on you are supposed to fill electrons here. While filling up of electron, you need to follow some standard rules. As I said, Hund's rule is also one of the important. Pairing of electron starts after each atomic orbitals are filled with one electron only, and atomic orbitals should be of the same energy. Here 1s we have and here is also 1s, but the energy is different. Paulis exclusion principle you need to follow. Electrons of opposite spin can only be paired. So out of 4 electrons, so 2 electrons I represent here. Okay, so remaining 2 electrons are going to fill in the anti-bonding molecular orbitals. I have not mentioned here. In 1s we have 2 electrons actually, and in this 1s also we have 2 electrons. So 2 plus 2, 4 electrons, and 4 electrons has to be distributed in this fashion here. So now we'll calculate, we'll write the electronic configuration here. So we have a sigma 1s. In sigma 1s we have 2 electrons, so superscript I write 2, and next one is a sigma star 1s, and there also we have 2 electrons. I am going to write it 2. That is the electronic configuration of helium molecule. And what about the bond order? We'll see. Bond order, which is equals to 1 divided by 2 into number of electrons in BMO. This is the BMO and this is the ABMO. BMO we have 2 electrons minus number of electrons in ABMO. There also we have 2 electrons. So 2 minus 2, 0 we are going to get. Therefore the bond order is 0. Remember that. In the previous case of hydrogen molecule, we got bond order is 1, means 1 covalent bond is present in between the hydrogen atoms. Since in case of He2, 0 bond order, means no covalent bond we have. So what it indicates, there is no existence of helium molecule. So helium molecule does not exist. Since the bond order is 0, means there is no shared pair of electron in between helium and helium. Therefore helium molecule does not exist, or one more way you can say, this is a monoatomic in nature. This is a monoatomic. This is not a diatomic molecule. Atomicity is 1 actually. So this is not a diatomic molecule, this is monoatomic you can say. In particular, He2 molecule does not exist in nature since the bond order is 0. If it does not exist means there is no question of paramagnetism and diamagnetism property of that. That is MOT of helium. Second one more example we'll see, the third one. And in the third one, I am going to consider example of Li2, lithium molecule, Li2. So we'll analyze the MOT of that. So as we know, one lithium combines with one more lithium, we get lithium molecule. Atomic number is 3. Therefore, the electronic configuration will be 1s2 and 2s1 here. In this case, 1s2 and 2s1. So total number of electrons, 3 electrons from this lithium and 3 electrons from this lithium. Totally we have 6 electrons, remember here. So 6 electrons has to be filled in the molecular orbitals. What are the atomic orbitals are involved? 1s2 we have and 2s2 we have. Here also we have 1s2 and 2s2. 1s atomic orbital combines with 1s atomic orbital, 2s atomic orbital combines with the 2s atomic orbital. So let me draw the energy level diagram of that. So here, this is for the 1s. Atomic orbitals, right? This is 1s and this is 1s. From 1s you get 2 molecular orbitals like this, right? And this will be BMO sigma and this will be ABMO sigma star, and this is also 1s and this is also 1s. 1s I have mentioned. So 2s also we have here in this case. So therefore 2s atomic orbital I am going to consider. So this is the atomic orbital and this is the one more atomic orbital, and these two are 2s. So 2s and 2s. From that you get 2 molecular orbitals BMO and ABMO. This is a sigma and this is a sigma star. This is for 2s and this is also for 2s since the combining atomic orbitals are 2s, and energy will be increasing in this fashion. Okay, so now we'll fill the electrons first in the atomic orbitals. So 1s2, so here we have 2 electrons. So in the one more lithium 1s2 we have 2 electrons here, right? So in a 2s1, in this 2s we have 1 electron, and this one more 2s we have 1 electron. Okay, so this lithium is this atomic orbital, and one more lithium, one more atomic orbital. In the middle we have molecular orbitals. So first let me talk about 1s molecular orbital. So totally 1, 2, 3, 4 electrons we have. So 4 electrons has to be filled. So lower energy level has to be filled first. So 2 electron and 2 more electron, 4 electrons we filled. So completely filled. So next, in case of 2s, 1 electron here and 1 electron here. Total number of electrons here are 2. So we have to fill 2 electrons. So 2 electrons I fill here itself. Okay, Paulis exclusion principle. So sigma 2s we are going to get 2 electrons, whereas the sigma star 2s that will be empty. In ABMO we don't have any electrons here. If we have 3 electrons I would have shown here. If we have 4 electrons I would have shown 2 electrons here. Since we have only 2 electrons, therefore lower energy level has to be filled first. Therefore sigma 2s is going to be filled. That is the energy level diagram. We'll write the electronic configuration. So now I am going to write here electronic configuration. So we have a sigma 1s, and in sigma 1s we have 2 electrons. We have a sigma star 1s. In this also we have 2 electrons. Later we have sigma 2s. I will continue here. Sigma 2s, and here we have 2 electrons. And in a sigma star 2s we don't have electrons. I am going to leave as it. This is the one way of writing electronic representation, electronic configuration. One more way I will tell you, that is, or I can consider, since if you observe, so this is the K shell and this is also K shell. As we know, principal quantum number is 1, principal quantum number is 2. So 2, that would be L shell. In this case, K shells are completely filled. Therefore, K shell does not participate in bonding, and it is not compulsory to mention 1s also. You can skip this part also, and instead of that we can write K shell are completely filled, therefore does not participate in bonding, and we can directly mention 2s also. One more way I mentioned, in that case the electronic configuration I write K and K, because this is the one K shell, this is the one K shell, both are K shells itself, they are completely filled. K, this is over. Next I write here, what is that, sigma 2s2. This is the one more way of writing electronic configuration if you don't want to mention 1s atomic orbital. Next we will see the bond order. What is the bond order in case of Li2? So half of number of electrons in BMO. So this is a BMO and this is a BMO. So this is a BMO and this is a BMO. So in BMO we have 2 electrons and 2 electrons, totally 4 electrons we have, 4 minus this is a BMO, isn't it? So this is a BMO, in this is also a BMO, but we don't have electrons, so 2 electrons we have, therefore 2 I am going to write here, and you will get 2 by 2 which is equals to 1. What that significance? In between 2 lithium atoms we have 1 covalent bond. Therefore, Li single bond, Li we are going to get. So bond order is 1 in case of Li2. So now we'll identify whether this compound, this molecule is paramagnetic or diamagnetic. As I mentioned, you need to observe the unpaired electrons in the molecular orbital completely filled, completely filled, completely filled. There is no presence of unpaired electrons. Because of this reason I can say this compound is diamagnetic in nature. Diamagnetic in nature since absence of unpaired electrons. So this is how helium molecule as well as lithium molecule I consider. That is about how we can explain the molecular orbital theory. Example 4, Be2 I am going to consider. Fourth one, beryllium molecule, Be2. One beryllium combines with one more beryllium atom, we get beryllium molecule. Atomic number is 4. Electronic configuration 1s2, 2s2. For this also 1s2, 2s2. From this beryllium we have 4 electrons, and one more beryllium atom we have 4 electrons. Totally 8 electrons has to be distributed. In Be2 we have totally 8 electrons. So 8 electron has to be distributed among these atomic orbitals. So let me consider the energy level diagram. We need to consider 1s as well as 2s, both energy diagrams. So let me consider here. So I am going to draw the 1s orbital. One atomic orbital in the left side and one atomic orbital in the left side. This is for 1s and this is also 1s, and these two will combine, we get 2 molecular orbitals. This is BMO sigma and this is ABMO sigma star. This is of 1s, this is also of 1s. So 1s is over now. Now let me construct the diagram of 2s. This is for the 2s, this is also for the 2s, and 2 molecular orbitals we get. This is BMO sigma, ABMO sigma star. This is for 2s and this is for 2s, and energy will be in this fashion. We'll distribute the electrons first in the atomic orbitals. So 1s2 we have, here also 1s2 we have. So in 1s atomic orbital we have 2 electrons of opposite spin. Whereas in case of 2s, here also we have 2 electrons. So let me draw the 2 electrons in this case. So in 1s molecular orbitals we need to distribute 4 electrons, 2 from here and 2 from here. 4 electrons we have, and this is how the 2 molecular orbitals are filled. In a 2s also we have 2 electrons from here, 2 electrons from here. 4 electrons has to be distributed in molecular orbitals like this. So that is about the energy level diagram. So we'll write the electronic configuration. We'll write the electronic configuration of this. I told you that In this case also the K shell is completely filled. So this is a completely filled. You can write K and you can write the remaining electronic configuration, or you can write the same terms what I told. To write the electronic configuration, both are considered. So I will write K and K, means the K shell and K shell, they are completely filled. Therefore I will move with this one. So we have a sigma 2s, and in that molecular orbital we have 2 electrons, superscript 2 I write, and one more we have where we have electrons, that is ABMO sigma star 2s, and in that case also we have 2 electrons. So that is the electronic configuration according to MOT. Will go for bond order. So bond order in Be2, that is 1 by 2 into number of electrons in BMO. Okay, so this is BMO and this is BMO, totally 4 electrons we have. So 4 electrons I mentioned, minus ABMO. So this is ABMO and this is also ABMO. In that also we have 4 electrons. So now the bond order we got 0. Since bond order is 0, therefore this molecule does not exist. This molecule does not exist, or you can say monoatomic in nature. This is not a diatomic molecule. Since we got a bond order 0, therefore there is no existence of a molecule like a Be2. That is the 4th example, Be2 about molecular orbital theory. Example 5, C2 molecule. One carbon combines with one more carbon, we get C2. Atomic number is 6, electron 6, electronic configuration 1s2, 2s2, 2p2 for the first carbon. And for this carbon 1s2, 2s2, 2p2 we have 6 electrons from here, 6 electrons from here. Total we have 12 electrons. Remember, 12 electrons we have. So 12 electrons has to be distributed in molecular orbitals. So remember here, in this particular example, we need to consider 1s as well as 2s as well as 2p also. 2p you are supposed to add here. Let me draw the energy level diagram of that. So see here, this is for 1s, and I hope 1s and 2s we are quite good in drawing the energy level diagram. This is for the 1s, and one BMO we get and one ABMO we get. This is sigma and this is sigma star. This is also 1s and this is also 1s. Energy level diagram of 1s. So now I consider one more, that is 2s also we have. So let me draw the structures. This is for the 2s. In a 2s we have one atomic orbital over here and one atomic orbital. We get 2 molecular orbitals. This is 2s, this is 2s, this is sigma, this is sigma star, and 2s and 2s I am going to consider. So 1s is over, 2s is over. You need to consider 2p also. So since 2p atomic orbitals are going to be involved, so let me draw above, because as we know energy will be moving in this fashion. So higher energy level I need to consider, and now here I am going to draw the structure of P. So for P we have 3 atomic orbitals, Px, Py, Pz, and for one more carbon we have 3 atomic orbitals, Px, Py, Pz. This is for 2p and this is also for 2p. So the molecular orbitals, so here we have one and here we have 2 molecular orbitals. So now we need to think over this. So remember, as I mentioned, carbon is lighter element. In that case, you need to consider the molecular orbitals in this fashion. I told you that one in general. If it is for oxygen, I would have reversed this. So 2 I am going to draw and 1 I am going to draw. The reason I told you that the mixing of 2pz and 2s atomic orbital. Therefore, for lighter, this is the fashion how we need to mention the molecular orbitals. So now, this is pi, these two are pi, and this is the sigma as we know. So here I will write pi 2px and this is pi 2py. Pi because there will be sideway overlapping of x atomic orbital and py atomic orbital. And this one, let me write, this is sigma 2pz, head-on overlapping of a pz, therefore sigma 2pz, and these three are bonding molecular orbitals. So next I will come to anti-bonding molecular orbital. These two are pi, therefore I will write pi 2px star I mention, and this is pi 2py star, and the above what we have, that is sigma star 2pz. So these three are bonding and above three are anti-bonding molecular orbitals. That is the empty energy level diagram. Now we have to fill the electrons 1s2, 1s2. In both 1s we have 2 electrons. So totally 4 electrons we have to distribute in this section. Therefore 1, 2, 3, 4. K shell is completely filled. Next I will come to 2s2 and 2s2. In a 2s2 we have 2 electrons. In one more 2s2 we have 2 electrons, and totally 4 electrons I am going to fill here. 2s is also completely filled. Now you come to 2p here and 2p here. In a 2p we have 2 electrons. Therefore in a 2p we have 2 electrons, and I write 1 electrons in these 2 atomic orbital according to Hund's rule. We have to fill all the atomic orbitals of same energy with 1 electron, and after that if you have extra electron, pairing of electrons starts. So therefore 2p I mentioned 2 electrons, and in this case also 2p I am going to mention 2 electrons. Totally how many electrons we got? Totally we got to 4 electrons. So 4 electrons we have, and 4 electrons has to be filled here. So totally 4 electrons, and out of those two, 1 and 2 I am going to fill here. As we know, the energy of pi x and pi y are identical. Therefore 1 and 1 I am going to fill. 2 more electrons we have, and 2 more electrons I am going to fill in this case. There is no electrons in case of a sigma 2pz and any anti-bonding molecular orbitals. That is the energy level diagram of C2. Now we will write the electronic configuration. Electronic configuration I write here. Since this is a K shell, okay, and this is a K shell, isn't it? 2 and 2, that is the L shell, the next one. Since K shell is completely filled, so therefore what I am going to write here, K. So these two are completely filled. K shell completely filled. Next we have sigma 2s. Sigma 2s, 2 electrons we have there, and next we have sigma star. Sigma star 2s, we have 2 electrons over there, and now you see we have pi 2px. So pi 2px, how many electrons we have? In that case we have 2 electrons, and one more is pi 2py. In that case also 2 electrons, and there is no presence of any electrons. That is the electronic configuration of C2. We'll see the bond order. Bond order, which is equals to 1 divided by 2 into electrons in a BMO. This is the bonding molecular orbital, this is the bonding molecular orbital, and these two are the bonding molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 bonding orbitals we got, minus. So anti-bonding molecular orbitals, this is the anti-bonding molecular orbital, and this is the anti-bonding orbitals. We don't have any electrons in anti-bonding molecular orbitals. Therefore 1, 2, 3, 4. 4 electrons we got here. So if you simplify this, we get 4 divided by 2, which is equals to 2. Bond order of C2 is 2. What it indicates? We have C, double bond C. Bond order in a C2 is 2. Therefore, 2 covalent bonds are present between combining carbon atoms. Whether it is diamagnetic or paramagnetic. And if you observe here, and we don't have any unpaired electrons, and because of this I can say this particular molecule is diamagnetic in nature. So this is how we can explain the MOT of C2. But remember, since carbon is a lighter element, so pi 2px pi 2p, why you need to write first, later 2pz you are supposed to write. If it is oxygen, I would have reversed this. That is the only change what you need to consider, and electron distribution takes place according to the standard rule, that is MOT of C2 molecule.